Hi, today for heat transfer we are going to look at lab 5, which is parallel and counterflow. Before going any further, let me introduce our team members. Our team consists of 4 people, which is Muhammad Amir Irfan bin Muhammad Shukri, MUHSIN AMILI bin NOOR, me, RUSHAN, anak laki Ranganathan, and also Muhammad AIMAN bin RAZAK. Next, let us look at the table of content. Our lab consists of theory, objective, equipment and apparatus, procedures and methodology, safety and precautions, results, discussion, and also conclusion. Okay, let us look at the theory part. Okay, for the parallel and counterflow, we are going to look at a heat exchanger. So before that, let me ask you: do you know what is a heat exchanger? Okay, a heat exchanger is a device for transferring thermal energy, which is heat from one fluid, either liquid or gas, to another. When the two fluids are physically separated, example of when the two fluids are physically separated, example of heat exchangers are radiators, which are found in cars, evaporators, and also condensers, which are normally found in aircons. Okay, what is parallel and counterflow? A counterflow is when the direction of the flow of one of the working fluid is opposite to the direction to the flow of the other fluid. When you see counterflow, it's just basically like opposite fluid which flows in opposite direction. Okay. And then in parallel flow, both fluids flow in the heat exchanger in the same direction. Okay, to your right, you're able to see the difference between the heat exchanger tubes which are in parallel and also counterflow. Okay, at the top part, the parallel flow, you can see both fluids flow in the same direction, which is towards the right. And for the counterflow, you are able to see that both fluids flow in opposite direction. One goes towards the left and another one goes towards the right. Okay, the objective of the experiment for parallel and counterflow is to investigate the effect of the control parameters and the heat exchanger configuration on the rate of heat transfer, which is our Q, and the overall heat transfer coefficient, which is our U. And it is also used to investigate the dependence of convective heat transfer coefficient on the Nusselt value and the flow geometry, because when you talk about flow geometry, different heat exchangers have different flow geometry, and by modifying this parallel and counterflow, we are able to provide a more efficient system.
Hi, Assalamualaikum. My name is Muhammad RAZAK. So this is the safety precaution for this lab. First, there is no food or drinks are allowed. Proper PPE and lab attire is to be worn at all times. Stay focused and aware of your surroundings. Do not play around in the work area. Ensure work area is clean and tidy during and after work is done. And then if there is any accident happen during the laboratory session, inform to the engineer in charge. Check all joints and connection of the apparatus before starting the lab work. Follow all safety operating procedure equipment before starting the experiment. Wear gloves when handling any heat. And lastly, maintain safe distance and sanitize hands before and after using any equipment.
Hi, today we are going to see at parallel and counterflow. Firstly, you should on the water supply. Next, we on the machine. Next, we press fill the tank, and then we on the pump. Okay, once the pump is on, we have to check our configuration first before starting the experiment. Either it is in counterflow or parallel flow. And for now, this is in counterflow. Next, we'll conduct the experiment by using the parallel flow connection. Parallel flow is when
this goes here and this goes here.
Assalamualaikum. Hari ini today we are going to conduct the heat exchanger experiment. Now this machine in the counterflow, you can see why it's counterflow because the cold supply will going to connect to the return supply, so it's going to counterflow. If it parallel flow, it's going to cold supply go to the hot supply. That's we know that is a parallel flow. Look at it. First, we are going to let the temperature stabilize at 60 degrees. After that, we are going to take the temperature by adjusting this water flow knob to 3 liter per minute, 2 and 1 and 0.5. To do it, we have to each flow we have to let the temperature stabilize. Then we take the data. Then we repeat the procedure.
So this is our result. So we've done 4 tests for parallel and counterflow. Bear in mind that heater temperature for this experiment is constant, which is 60 degrees Celsius, and each test we run with different flow rate for cold flow, which is 3 liter per minute for test 1, 2 liter per minute for test 2, 1 liter per minute for test 3, and 0.5 liter per minute for test 4. After we record all the temperature for hot and cold circuit, we find the temperature difference between TH2, TH1 and TC2, TC1. After that, we calculate the average temperature for hot and cold circuit by dividing the sum of TH1, TH2 and TC1, TC2 by 2. After that, by using the formula given in the additional information, we calculate the temperature efficiency of hot and cold circuit of the heat exchanger and the mean temperature efficiency of the two circuits. Next, we calculate the value of water density for hot and cold circuit. As you can see, the water density for cold circuit is higher than hot circuit. And then we calculate the specific heat for each circuit and then the heat transfer rate QE and QA. We are using the value of QE and QA to calculate energy balance coefficient CEB. And then we repeat the same step for counterflow experiment, and this is the result that we gain, and we calculate.
Hello, my name is IRFAN. So today we talk about LED parallel and counterflow. So I start with discussion number 1. It asks us to create a profile chart for each flow using the input and output temperature TH1, TH2, TC1 and TC2. So to sketch for both parallel and counterflow, so we put for x-axis is position and y-axis is temperature. So as you can see, here the chart for parallel and counterflow. Next is from the chart, we must calculate the water density for hot pH and cool water circuit TC at each flow rate and the specific heat capacity for each circuit at each flow rate. As you can see, this is the formula for the water density. So we take the data, put in the formula, and for pH1 we get 985.6 and pH2 we get 985.0 and pH3 we get 984.1 and pH4 we get 983.3. Next is for PC1 we get 996.7, PC2 996.1, PC3 995.6 And lastly, PC4, 994.5. So next, for calculation for counterflow. For question 2, based on information in the result table, create a chart of energy balance coefficient, vertical axis, against heater temperature. So this is calculation to find energy balance coefficient. And this is a chart for parallel and counterflow. As you can see, this is according to the table, we put according to the data. So according to table data, so we put the data according to the table, we put the data and we make the chart for parallel and so this is the chart. As you can see, this is the table. So we put the data. After that, we make the chart for energy balance coefficient versus the temperature. That's all from me. Thank you.
Assalamualaikum to Professor Zahir. My name is MUHSIN bin Rosli. Today I'm going to present the discussion number 3. So the discussion number 3 asks us to find the LMTD and use this to calculate heat transfer coefficient for each heater temperature. So we have the formula for LMTD, which is TH2 minus TC2 minus TH1 minus TC2 over ln TH2 minus TC2 over TH1 minus TC1. And the formula for heat transfer coefficient, which is QE over area time LMTD. So proceed with the calculation for the parallel flow. For the test 1, we have to calculate the LMTD with the help of the data we have. So we get 28.68 degrees Celsius. Then the volume of LMTD we can plug in the formula of heat transfer coefficient, which is QE over area time the LMTD, which is 28.68 degrees Celsius. So we get 272.93372.07. So we can see more clearly in the test 2. We have TH1, TH2, TC1, TC2. We can put in the LMTD formula. We get 27.87 degrees Celsius. Then we can calculate the U QE over A times 27.87, which is LMTD. We get 23,515,608.18. So it goes the same with test 3 and test 4. We have to calculate both LMTD and the heat transfer coefficient. So in the conclusion, we have to calculate LMTD, so we can proceed to calculate the heat transfer coefficient. So for the counterflow, also the same. With the help of the TH1, TH2, TC1, TC2, we can calculate the LMTD. So we get 27.05 for test 1. Then the LMTD we plug in the heat transfer coefficient. We get 27762422501. So for the test 2, it's the same also. We calculate the LMTD. We get the temperature, which is 23.31 degrees Celsius. Then we put in the heat transfer coefficient. We get 13852,758.71. So for the test 3 and the test 4, also the same with the first 2 tests. With the help of from information we have, TH1, TH2, TC1, TC2, we can calculate the LMTD. Then we can calculate the heat transfer coefficient. So for the test 3, LMTD is 25.90 And test 3 for heat transfer coefficient is 19769.264.6. And the test 4 LMTD is 24.12. And the test 4 for heat transfer coefficient value is 1857530.34. So for the next discussion is compare the heat transfer coefficient of the two heat exchanger. So this is the configuration with the high heat transfer coefficient, show that the heat is well conducted in the system and has good heat transfer coefficient. As you can see, the parallel configuration and counter configuration have a little bit different between them. The configuration of Counterflow is a little bit lower than parallel configuration. So that's all for me. Thank you and Assalamualaikum warahmatullahi wabarakatuh.
So our conclusion for these laboratory activities, we evaluate and study the overall heat transfer coefficient, log mean temperature difference LMTD, heat transfer and heat loss for energy balance. We were able to evaluate heat exchanger performance at two different configurations. In parallel flow configuration, the exit temperature of the fluid is always higher than the exit temperature of the cold fluid. For counterflow, the hot temperature for the exit fluid is lesser than the exit temperature at the cold. The LMTD for parallel is higher than the counter current flow. However, the overall heat transfer coefficient for counter current flow is higher than co-current flow. Counter current flow configuration of heat exchanger is more preferred for practical application. One of the application of heat exchanger is oil cooler. Lastly, when the flow rate of one of the stream increases, the rate of heat transfer will also increases. The amount of heat loss from the hot water is not equal to the heat gained by the cold water due to the heat loss to the surrounding. That's all from us. Thank you very much.